So now we are transitioning to the technical session 2. We are glad to have our speaker with us now. A warm welcome to you, sir. Now, before we begin, I would like to introduce our resource person for this session. This session will be delivered by Mr. Deo Nath Jha, Chief Manager at the Power Grid Corporation of India Limited. With over 11 years of experience in EHV asset management and digitalization initiatives, he holds a BTech in electrical engineering from IIT Dhanbad and a PG diploma in AI and machine learning from IIIT Bengaluru. Mr. Jha has contributed to major initiatives in asset performance management, advanced diagnostics, and AI-driven digital platforms, and has authored papers at IEEE, CIGRE, and other international forums. He is also a recipient of the ISGF Innovation Award in 2024 and 2025. His topic for this session is Future-Ready Energy Infrastructure, Digitalization, Renewables, and Decarbonization Pathways. Sir, we welcome you and request you to kindly take over the session. Sir, please.
Thank you, ma'am. Good evening, everyone. So, I hope my voice is clear.
Voice is audible.
So, this session is on future-ready energy infrastructure, digitization, renewables, and decarbonization pathways in India. Before we look on what is the future-ready energy infrastructure being created in India, we should have a look on what energy infrastructure is already there and how we have progressed over the years since independence. So Indian power sector from 1947 to 2025 has come from about 1 gigawatt to 509 gigawatt of installed capacity now. The per capita consumption has risen about 95 folds from 16 kilowatt per hour during independence to 1538 kilowatt hours now. And now we also have an inter-regional capacity of 118,000 megawatt. Moving ahead in 2030, we are planning to have 820 gigawatt installed capacity, 2,000 kilowatt hour per capita consumption, and around 30,000 megawatt increase in inter-regional capacity. So how did we come here? Electricity in India started from 1879 when the first demonstration of electric light was conducted in Kolkata. From a single light to a single substation, we moved in 18 years when first substation was created at Darjeeling in 1897. From first substation, we moved to a transmission substation within 2 years in 1899 when the first thermal power station was established at Princep Ghat Imambagh Power Station, and it had a power capacity of 370 kilowatt. The first transformer that was manufactured in India was in 1936, manufactured by Government Electric Factory at Bengaluru. It was a 10 MVA transformer at 132 kV level. Then first high voltage transmission assets in India, the 1949 first 132 kV line at Sibrampalli, Hyderabad transmission line. Then we moved from 132 to 220 kV level in 1960 with the commissioning of Bhakra, Gangobal, Ambala, Panipat, Delhi line. This was basically a Bhakra Delhi line with 3 interconnections in between created by BBMB. And in 1965, we also had our first 220 kV indigenous transformer commissioned by BHEL, commissioned at Koradi, Maharashtra. Then in 1977, our country moved from 220 kV up to 400 kV EHV level. And the first transformer was commissioned at Panipat by BBMB, supplying power to various districts in Haryana. Then in 1978, the first 400 kV line came up as Obra Sultanpur in UP. And then in 1980, our first HVDC was established, and that is 100 kilovolt, Barsul Lower Sileru in Himachal. These are the photographs, the Sultanpur substation in UP. It was also Asia's oldest 400 kV substation, the first 400 kV substation in Asia. Then in 2007, we established the Sipat Sivni link, which was the first 765 kV transmission link in India. And from 765 kV to we moved to 1200 kV in 2012. This is the world's first transformer and transmission system established at 1200 kV. It was installed at Bina, and it was a test station. And also a loop-in, loop-out 1200 kV transmission line was established at Bina, which went from Bina to the National High Power Test Laboratory. And this is still the world's highest operational voltage level. There are power assets above this voltage level existing in world, but they are all in laboratory. They're not. This is the highest voltage level assets that are deployed in the field. And before this, the highest was 1100 kV, the Russia line, the Russia-Kazakhstan line, but that has been decommissioned in 1991. So after that, this is the highest kV voltage level still in operation in the world. Then there's also been an evolution of gas insulated systems now in India. When we started with 220 kV gas insulated system at Kankulam in August 98, 10 years later, we moved on to 400 kV GIS at Maharani Bagh. Then after 8 years, we had GIS at 765 kV. The first was at Pune in Shikrapur locality. And then in December 2020, our first hybrid GIS, that is a station with a combination of air insulated switchgear and gas insulated switchgear, that was established at Ballabgarh. Now, why these gas insulated systems have come up in much vogue now in India is because of more and more number of these power centers or substations are coming up in urban areas where land acquisition is a very big issue, and we have to create these substations in a congested spaces. So our country has gone ahead with planning of gas insulated switchgear, which require about 1/3 space than an air insulated systems. So the Indian power transmission grid has multiple voltage levels. The HVDC voltage levels are 800 kV, 500 kV, and 320 kV. Similarly, AC voltage levels range from 66 kV to 765 kV. Below 66 kV, the Indian grid, the voltage levels are termed as distribution level voltage levels. So they are 33 kV, 11 kV, then 440 volts, 110 volts. All these are distribution level voltage levels. Total transmission line length in India is around 5 lakh circuit kilometers. Total transformation capacity, that is substation capacity, is around 13 lakh MVAs, and total interregional capacity in India is 1,18,740 megawatt. Interregional capacity is the capacity of the lines that are transmitting power between different regions. So India is divided into 5 electrical regions: north, east, south, west, and northeast. So the lines interconnecting two different regions have this much power carrying capacity in India now. Now this is how our national transmission grid has evolved. So pre 1991, we had 5 different regional grids operating at 5 different frequencies. So the frequencies ranged from about 48 hertz to 52 hertz between different regions. In October 1991, the first time we interconnected 2 different grids, that was east and northeast grids, were synchronized from the Tala transmission network. That is, the connection was established between Siliguri in West Bengal to Purnia in Bihar. And that's how the eastern region and northeastern region grid was connected. In March 2003, the western region was further connected to this ER-NER grid, and it was synchronized in March 2003. It was synchronized through Rourkela. The line was connected from Rourkela in Orissa to Raigarh in Chhattisgarh. Then in August 2006, the northern region was connected to this grid, and this was called as a new grid, means north, east, west, northeast. And this was connected through the connection of Gwalior Agra line. For many years, Gwalior Agra was the single line which was connecting northern region to the other regions. Still, about for 7 8 years, this was the single line which was connecting northern region to the other regions. Then in 1991,
Sir, you are muted. Please turn on your mic, please.
No voice.
Jha sir, you are muted. Please.
is my voice audible now?
Yes, yes, you are.
So yeah, shall I start again the presentation? Hello.
You can start right now. No problem.
Okay.
From this slide, you can start.
Okay, from this slide. So in 1991, before 1991, our grid was divided into 5 regional grids with 5 different frequencies. And the frequencies ranged from about 48 to 52 Hz in different transmission in different regional grids. Then in 1991, for the first time, we interconnected 2 different grids, that is the eastern region and northeastern region. And it was connected through the line that was Siliguri in West Bengal to Purnia in Bihar. In March 2003, the western region was connected with this northeastern region grid, and it was connected through Rourkela in Orissa to transmission line to Raigarh in Chhattisgarh. Then in August 2006, the northern region was connected to this western, eastern, northeastern grid. This was connected through the Gwalior Agra line. And for many years, Gwalior Agra was the single source of supply for the northern region. Means the power was generated in western region through coal-based generation, and that power was supplied to northern region through this Gwalior Agra line. Then in December 2013, we connected the southern grid to the rest of the interconnected grid. And this was done through charging of Raichur-Sholapur line. Raichur was in Karnataka and Sholapur was in Maharashtra. Then in January 2019, the Leh region in Ladakh area was connected with this national grids through charging of Srinagar-Leh transmission system. So this is a complete journey of 28 years by which we have created a one nation, one grid, one frequency type of system. And this is the largest synchronous grid in the world. So why we call it largest? Because it has more than 11 lakh node points connected at a single frequency all across India. And why is this important? Because once we have more and more networks coming at a single frequency, the chances of grid disturbance gets lower and lower as the grid gets stronger. So if any node of supply goes down, there are multiple parallel paths to feed that particular node of supply. So the frequency will not get disbalanced in case of any outages. So presently our interregional capacity is 1,18,000 megawatt. By 2030, we are planning it to increase it to 1,38,000 megawatts. Then we also have some international connections, like India is connected with Nepal. In the earlier session, I heard the speaker talking about SARC grid. So in our power sector domain, we call it as a South Asian energy ring. And because we are not connected with Pakistan and Afghanistan, there are also no plans to connect. So we do not call it a SARC grid as now. It is a South Asian energy ring where we are getting connected to Nepal. There are more than 16 links connecting India and Nepal. Most prominent of them is 400 kV Muzaffarpur Dhalke Bar. Other links are at 132 kV or lower levels. Now we are also connecting Gorakhpur in Uttar Pradesh with Nepal at a 400 kV level. That is Gorakhpur Butwal line. It is going to come up shortly in a few months. Then we also have multiple transmission links with Bhutan. And Bhutan is a net energy exporter to India. Means we import energy from Bhutan, the hydro-based energy. And for many years, the entire North Bengal region was powered by this energy imported from Bhutan through Tala transmission network or the Chukha transmission network. So both these stations are in Bhutan area. These are the prominent lines that are connecting Bhutan to India. Then currently between India and Myanmar, there is a transmission line at 11 kV that is Tamu More in Manipur. And there is also an HVDC network planned with Myanmar that is going to come up in the next few years. And India, Bangladesh is connected by two transmission lines, that is 400 kV Berhampur Behramara from Bengal to Bangladesh, and one connection goes from Tripura to Bangladesh, that is 132 kV Komla Surajmani Nagar. Then we have also been planning India Sri Lanka interconnection, that is an HVDC network connecting Madurai in Tamil Nadu to Anuradhapura or Kandy in Sri Lanka, and this will be done at 320 kV HVDC levels. Then so India Sri Lanka connection is already, the engineering has been done and the DPR has been finalized, and now just the final signing stage is to commence. Then studies have also been undergoing for India Maldives connection at 320 kV HVDC level. So Kochi in Kerala will get connected to Male in Maldives and via an undersea HVDC link. And then there is also a proposal for India Oman HVDC connection, where Gujarat will be directly connected with Muscat in Oman. And so we will explain why these interconnections are going to come up, and what is the need, and how India will benefit through these interconnections with other countries. Apart from this, there are also plans to connect India with Singapore, the transmission network. So India Andaman will get connected, and then from Andaman there will be a line going to Singapore. But this will take about around 15 to 20 years to build up. So now we come to Power Grid, which is India's national transmission utility. So we have around 1,560 transmission lines across 181,492 circuit kilometers. These are all the asset numbers. 287 EHV class substations, 5 lakh MVA. Earlier we saw that India had total 13 lakh MVA capacity, out of which around 6 lakh is fed up by Power Grid. So Power Grid carries around 45% of India's electricity. And in national transmission, we have certain new technologies, like there are 19 HVDC stations. There are 765 kV stations, which make India's grid as the world's largest 765 kV transmission network. Then there are 170 numbers 400 kV stations, also 22 SVC and STATCOMs. Again, SVC and STATCOMs that are present in India are the highest number that are there in the world at EHV level. Then there are 84 numbers GIS or hybrid stations, more than 292,000 towers, and 4,200 transformers and reactors above 400 kV level. So now we see how previously we have seen how we have moved from 6 kV to 1200 kV in about 100 years. Now we are going to see what are the new technologies that are coming up in power transmission sector. So major technology milestones. Then our first back-to-back HVDC came up at Vindhyachal in 1989. Then there was an HVDC bipole link Rishan Dadri system that was established in 1990 to supply reliable power to Delhi. Then SVC was commissioned first in Kanpur at 140 MVAr. Then first GIS I've already talked about. First AIS was commissioned at Sivni, and then 1200 kV was developed at Bina. Then we established National Transmission Asset Management Center. So a single center which is responsible for monitoring and remote operations all the substations within Power Grid networks in 24. So this was done in 2014. Then in 2015, we commissioned the world's longest multi-terminal HVDC between Agra and Bishwanath Chariali. So multi-terminal, why it was longest? Because it covers 1,800 kilometers between Agra in Uttar Pradesh to Bishwanath Chariali, and one parallel line also goes to Alipurduar in Bengal. Then in 2020, India's first VSC-based HVDC link was commissioned between Pugalur and Thrissur. So what was the difference between this link and the earlier HVDCs was voltage source converter based. Earlier HVDC stations are LCC, that is line current commutation based. Voltage source converters provide better voltage stability for HVDC networks, and better voltage stability leads to better grid parameter control. Then in 2021, first natural ester-based 400 kV shunt reactor was commissioned at Mathan, very near to your Durgapur. Then in 2024, the Centralized Control and Protection Center was established in Manesar. So like NTMC, this centralized control and protection enables an engineer to change the relay and protection settings or control these settings sitting at a single point in India, and he can control these settings across all substations in India. Then our largest digital substation was commissioned at Navsari last year. And why it was the largest? Because it had more than 124 bay units, which were merging digitally together. So what are the improvements that we have seen in component-wise technologies? So we have seen improvements in core magnetic steel. We have seen improvements in winding insulation and insulating liquids, and also bushings in transformers. So core magnetic steel, in 1930s, we started with CRGO steel of thickness 0.3 mm. Then in 1970s, we reduced thickness to 0.3 mm, and it was highly permeable CRGO steel. And now in 2010s, we have this laser refined high permeable CRGO steel introduced at 0.23 mm. So what has this done is lesser the thickness of the steel laminations, more evenly distributed the voltages across the transformer core. And this laser refinement has led to reduction in manufacturing malpractices and unevenness of those laminations. So it has led to better transformation capacity and lower failures in transformers. So like earlier in 1980s or 1990s, our transformer failure rate used to be around 8 to 10% each year. Now the transformer failure rates are 0.6% or 0.7%. So last year it was 0.57% in a transmission network. So this has hugely reduced the magnetic component failures in transformers. In terms of winding insulation, the insulation paper was of kraft paper type, introduced for winding insulation in the early 1900s. In 2010s, we upgraded to thermally upgraded kraft paper. So it began to be introduced in converter transformers that are used for HVDC applications. And now they are also being used for transformers that are in RE pooling stations, and that are used to pool RE power in Western Rajasthan or Gujarat area. So what is the advantage with these thermally upgraded paper? Is that kraft paper has a thermal limit of around 110 degree. So once a transformer transformer has an oil system, a winding system, and more the loading is on transformer, the temperature keeps on rising inside the transformer. Once it goes above 110 degrees centigrade, failure can occur. But with thermally upgraded kraft paper, that temperature threshold increases up to 130 degree. So the transformers can be loaded more highly and more variably. Then in winding insulation in 1990s, we had this continuously transposed cable was introduced. And now in 2015, for smaller transformers, we have gone for introduction of paperless CTC. So the adoption of CTC brings advantage in reduction of eddy current losses. And in addition, it is possible to get more uniform distribution of temperature throughout the whole winding of the transformer. In terms of insulating fluid, normally all the transformers use mineral oil. The distribution transformers that you see in your localities and in your cities up to 11 kV also use the used vegetable oil as an insulation medium. But as the voltage goes up, the dielectric strength of the oil needs to be very high to withstand those high voltages. So in transmission EHV class transformers, we use uh, the uh, the processed mineral oil. Then in recent years, various alternative technologies have come up, like synthetic and natural esters and gas to liquid technologies. So the advantage of these oil with respect to mineral oil is that they have very high fire point and flash point. So like mineral oil catches, like earlier I talked about the temperature going high and transformer failing. So mineral oil catches fire once the temperature reaches about 160 degree inside the transformers. But these synthetic and natural esters have fire resistance capacity up to 300 or 300 degrees centigrade. So till 300 centigrade, there will be no fire in the transformer. So these are more safer to use in the urban, if the transformers are there in urban areas or in underground areas, like some 66 kV stations in urban regions are created underground or within localities. So now the government is pushing those the manufacturers or the utilities to use esters within those transformers to avoid the incidences of fire and subsequent damages. So in 2021, world's first 400 kV natural ester-based reactor was commissioned at Mathan, and Asia's first 400 kV synthetic ester-based transformers have now been commissioned in Bhiwari in just last week in January 26. In terms of bushings, the vast majority of installed power transformers are made with oil paper insulation. So inside a bushing, there will be a paper insulation, and the bushing will also be filled with oil as an insulating medium. So this is very reliable technology, but has important safety disadvantages, such as if the bushing fails, then the oil will spread across the transformer and it can lead to fire in the transformer. So nowadays, resin impregnated bushings have been introduced, where instead of oil, the bushings are filled with epoxy resins to avoid fire in the bushings or the transformer in case of any failure. So
Please mute your mic, please.
we have been using resin impregnated bushings up to 400 kV level. Now trial uses for the same have also been done at 765 kV levels. And now there is also technology to remove the paper inside the bushings, because we have used those bushings with resin impregnated synthetics. So instead of paper, normal paper, a synthetic compound is used and then again filled with resins to make the bushings more fireproof or more fire resilient. Then in growth in circuit breaker technology, earlier when electricity started in India, there were oil circuit breakers, open tank with upward motion operation. Then these are some photographs from earlier from CSC. Nowadays, then we moved to air blast breakers in 1960s, and then in 1990s and 2000s, SF6 circuit breakers were introduced in India. In terms of protection system, we used to have very bulky and huge relay systems. Nowadays, everything is microprocessor based and very small and compact, which has reduced to a reduction in the space required in the substations. So what are the factors leading to high asset management performance levels? So these were the technologies. Now, what are the practices? In terms of line maintenance, there has been a proliferation of drones or aerial vehicles for patrolling instead of foot patrolling. We are also using satellite image intelligence to know the condition of our transmission lines or other transmission assets. Then there are emergency restoration systems. So suppose if a transmission tower collapses or a conductor breaks, the line can be again brought back into service within 24 hours. And then there are also hotline maintenance systems up to 765 kV, which enables utilities to maintain the line without taking any outage or shutdown. Then within substation maintenance practices, we have gone for reliability centered maintenance. for different switchyard equipments. Then we have created these centralized remote operation centers, and at national level and at regional level, and various digital tools are used for monitoring of these substation assets. So why are we transitioning towards this digital technologies? Because uh, nowadays, with proliferation of many sensors and digital tools, the data volume for any asset is very huge. So, like within Power Grid itself, the condition maintenance data, the total size of condition maintenance data has risen from about 2 to 3 TB in 2020, and now it has come to about 35 TB in 2025. So there are very huge amount of data that is being collated, and new technologies like IoT sensors, like AI, like blockchain. Then there are new value chains and operation models that are coming up, and for business requirement that to optimize the performance and create new asset models. So how are we doing this? What are the technologies that are being used? Are Internet of Things in the IoT sensors, which are transmitting the real-time condition of assets to a central control center. Then process bus is used for digital substations. Then there is captive network for 5G applications enablement. A lot of these applications and the devices communicate on over 5G, and which is proliferated all over India. So we have this captive network to secure the communications. Then digital designs, that is 3D models are being utilized in construction stage. Then 3D printing, like we are using additive formulation to generate any spare parts or generate any mechanical parts for electrical systems indigenously rather than relying on any OEM or third party vendors for the same. Then we are also going for robotic and drone inspections. Digital twins are being created for the assets. Then augmented reality for remote assistance of experts, and cyber security through Security Operations Center. So this is Power Grid. I'll skip this due to paucity of time. So I'll directly go into the details of those technologies that was mentioned. So the National Transmission Asset Management Center, enables remote operation and monitoring of all substations from a centralized location. So how it is done is through IC 61850 protocols. Entire data of a substation is transmitted to a remote location, and it helps is in optimization of human resources. So there is no requirement of shift operations at substation. It enables faster restoration in case of tripping through online diagnostics of real-time parameters and disturbance records, and safe and secure operations with minimum human intervention. Then unified digital assessment of asset network. So the entire data is correlated from different sources and asset registers, and there is bird's eye view of management over asset performance issues and their management. Then this is a asset life management system. It is a patented system in Power Grid for health indexing of all the transformers and reactors. Then this is a digital application for routine patrolling assessment of network. So it is an in-house developed model and application for TL patrolling activities. It enables real-time monitoring of patrolling efficiency, and the personnel can real-time get notified about any issue in any of the transmission lines under their jurisdiction. Then we also have this image processing based defect identification in transmission line towers. So suppose a drone flies over a transmission line. Earlier, what used to happen is it used to collect multiple images of those assets, and then a person at the office had to go through those images to identify the defects. But now through AI-based image processing, there are more than 20 types of defects that are being identified in ground patrolling in real-time basis, and more than 12 types of defects in drone patrolling. So when the drone is flying, the person at the ground is getting real-time alerts on whatever the defects the drone is observing. And the processing speed is very high, that is 400 photographs per minute, accuracy is more than 70%. Then we also have a program with digitally connected employees to enable intelligent inspection in Power Grid, that are AR-based digital headgear. So these headgears enable the experts sitting at remote locations to get connected to the on-site employee. So they both have a two-way vision. Whatever the site personnel is seeing through his eyes is getting reflected back to the expert on his screen, and whatever the expert is whatever the drawings, the schemas the expert is has on his laptop or computer is getting transmitted to the site personnel through this small eyepiece that you see. And then there is also tablet-based intelligent inspection, where end-to-end asset management is. So whatever the person, whenever someone goes to a site to attend an issue, he can record all the parameters remotely, and that gets transmitted to the central office in real time. Then the VR-based safety training. Safety is a major part of any utilities operations. So, and we have also introduced VR-based safety training modules, which have been developed to simulate critical work scenarios in a highly immersive and controlled environment. So as you can see, these modules are being used to train the personnel on how they have to use ladders to climb up above the towers. What are the CPR procedures if any fatal accidents occur? So any non-fatal accidents occur. What is the electrical maintenance of line terminal equipments, how they can do, and what is the safety and insulator string replacement. Then this is about the Wi-Fi that I talked about, a captive non-public network Wi-Fi that is being created across India, across the entire transmission network. Then satellite image intelligence, a trial project undertaken for 600 kilometers transmission line in NER. So instead of patrolling by drones or through human, we are using satellite imagery to capture the details on the tree growth beneath the transmission structures. What is the rate of growth, means how much they have grown in 3 months, 6 months, and then forecasting that growth levels on how quickly they will touch these transmission conductors, and then uh, the risk calculation is done and suitable maintenance tasks are created. So this is being done in collaboration with ISRO, development of spatial decision support system to leverage advanced satellite-based remote sensing and geospatial analytics for spatial risk mapping. Then, in terms of new technology, in Indian grid, this dynamic line loading systems have been introduced. So suppose earlier, like I take an example of Durgapur Mathan line, which is a very short line at 400 kV level, supplying about say about 250 MVA of transmission power. So it is a fixed. Till now, the concept was of transmission of fixed power across the transmission line. So if a line is rated at 250 MVA, it will supply that much power only. But now with the introduction of dynamic line loading, the more power you send across a transmission line, theoretically the sag, the line, more loading is on line, the sag will increase and the transmission conductor distance with the ground will decrease. But this dynamic line loading, what it enables us is to get real-time environmental conditions across the line. So if the ambient temperature is very low, if the wind speed is very low, then then the power flow across the line can be increased, and then we also get real-time updates on what is the sag or what is the distance from the ground, and based on that we can continuously increase the power flow across the line till a threshold level. So the capabilities are that it has real-time dynamic rating ensuring maximum average conductor temperature limits. Then there are also 7-day forecast, capacity forecast with 98% confidence. So sitting today on 12th January, I can know how much I can uh, till 19th January, how much power flow I can send across that transmission line, because I know the weather conditions that are forecasted 7 days ahead. And it enables increase in power flow capacity while avoiding overheating of the conductors or excess sag. And then I talked about digital substations. So whenever we hear of digital substation, the first question is what is digital in a substation. So this on the right hand side you'll see a picture where, if you ever visited the substation, then there are transmission equipments, then all the transmission equipments are the cables transmit data from equipments to control relay panels, which is in a relay room. And from relay panels, the data goes to a central control room through a station bus. So in a digital substation, when we say digital substation is when this entire process is digitized rather than manual or analog reading to be transferred from one equipment to other. So in 1990s, we started with substation automation system, where the controls room server of a station was digitized. Then relay rooms, these microprocessor relays were introduced around 2005 to 2010. So these CRP panels were digitized. And now in 2020, at process level, we have digitized the signal flow from equipment to a relay room. So the advantages are there is reduced copper requirements. So instead of multiple cables transmitting different signals, so for each signal you need to have one cable in the earlier regime. So if from a transformer, that temperature will go through a temperature reading will flow through a different cable, the voltage reading will flow through a different cable, the current reading will flow through a different cable. But now all of these is collated within a single fiber optic cable, which runs from all the equipments, a single cable collecting data from all the equipments in a substation. That single cable carries all this data to the relay panels, and it enables faster commissioning of assets and online testing. Then we also have this indigenously developed substation inspection robot, all-terrain robot for round-the-clock inspection of substation. It was developed jointly in collaboration with IIT Kanpur. So it utilizes AI algorithms to identify and flag any damages, cracks, or hotspots within the assets. And here you see the robot on the right-hand side. It is all-terrain because it can. So in a substation, there are multiple types of terrain like plain roads, the PCC roads. Then there are gravels at certain areas. Then there are also stairs within the control room building. So this robot has the ability to work on all these surfaces. And then here you see below the type of readings, the gauge readings that it can note, and the error that is below 5% in the readings that with the actual reading and what the robot has sensed. Then we are also using a hall inspection robot for HVDC systems. So in HVDC, if a HVDC station is charged, a person cannot go inside the wall. So for maintaining a wall, either it has to be taken under shutdown or the maintenance had to be postponed. But now with the introduction of these robotic platforms, these robots can take a look inside the wall even when it is in charged condition, take all the readings and then come back. So this has reduced the outages of these HVDC stations now. Then I was talking about 3D printing. So here in the image you see various 3D printed pressure relief devices which are installed in transformers. So, and it was also used to manufacture and repair cooler fan modules for a thyristor controlled for a TCSC at Raipur, thyristor controlled series capacitor. Then, so nowadays we are going for 3D printing of, if any mechanical component fails in a transmission equipment, we try to go for 3D printing of that equipment instead of going for a new buy of equipment. Then this is the reactor, the world's first 400 kV reactor with natural ester. It was commissioned at Mathan substation. Then in terms of rapid response teams, PowerGrid has been using these emergency restoration systems to quickly, safely, and efficiently restore power interrupted by natural disaster, sabotage, or vandalism. So you see this is the main transmission tower. And if the transmission tower collapses, then we can use these single mast pole with guide wires to temporarily restore the power flow across the transmission network. Then the hotline maintenance systems. So these are insulated bucket trucks. The person goes inside this bucket, and then the lifting of the boom, the person reaches up to the charged conductors or the charged assets which are being used, and this is being done for replacement, rectification, tightening of spacers, spacer damper systems in a transmission line, and also used to repair various assets in the substation. So this allows the person to repair or restore assets without taking any outage or shutdown of the equipments. Then, in terms of new technology, in terms of on-demand repairs, we have gone for now many of these high voltage equipments are being repaired at site with um, wi- uh, because of those high voltage testing kits now being available in India, which are ensuring the successful repair and charging of these assets at substation level itself. And through collaborative efforts with various vendors, we have also been successful in developing indigenous capacity in the field of AIS and GIS up to 765 kV, HVDC up to 800 kV, and RIP bushings and ERS towers up to 400 kV. So now all these things are available indigenously in India itself, and we are not dependent on any foreign country for sourcing these equipments. Then drone applications, like I told, drones are used for line patrolling and surveillance, and for insulator cleaning, pilot wire stringing, construction monitoring for 25 to 40 kilometers. Then new initiatives that are under development are mobile tower crane for mechanization of tower erection. So for the last few years, the focus was on automation of O&M systems, operation and maintenance systems, and transmission utilities. Now the focus is shifting towards mechanization of construction activities. So for that, like for tower transmission tower erection, we are going for mobile tower crane, and then we are also trying to go for indigenous development of gas insulated bus pipe for development of 765 kV class GIS equipment. Then also indigenous development of containerized high voltage setup. So till now we have high voltage setup in India only up to 400 kV level. That is a mobile high voltage setup which is available within substation. But now with this containerized high voltage setup, we are trying to go for mobile testing system within substations up to 765 kV. Then use of helicrane or helicopters in transmission tower construction. So these photographs that you see where the helicopter there, these are specialized helicopters which are used to lift very heavy transmission towers above and carry them above the hills or across the rivers for installation. So like the type of towers, like type of structures that you see is being carried by these helicopters is around 9 to 10 tons, which is very heavy for a group of people to carry across the hills through head loading. But these can be carried, so it takes about 10 to 15 days to carry a whole tower structure up the hill through by humans. But by using these helicopters, these structures can be an entire tower of around 120 tons can be carried above the hill within a few hours, or like about 3 to 4 hours. These things can be pulled up over the hills. So this leads to quickening of the transmission construction works. Now, in future roadmap, what are the new technologies in transmission? So the key trends that are shaping the energy utilities is the 4 Ds of energy transition: decarbonization, transitioning away from fossil fuel-based energy. So introduction of more and more renewable energy. Then digitalization. So we have seen a lot of digitalization now in the field of transmission, and also this is penetrating in the field of distribution with the introduction of smart meters, and with energy where the energy consumers are turning to prosumers. Then decentralization, like distributed energy resources like rooftop solar are proliferating, and deregulation, where the customer has his own choice on where from he can procure power, and the ownership of energy resources are diversifying. So what are the imperatives for Indian power sector in 2047? One is electricity supply is going to be based on renewables, storage, and nuclear transitions. Then industrial feedstock supply, the green hydrogen transition is going to come up in a big way in the next 10 to 20 years. and also bioenergy transitions for mobility and industry applications. Then there's fast-paced deployment of low-carbon energy technologies to meet rapidly growing energy demand. And then there is also a focus on development of indigenous advanced small modular reactor technologies for a scalable low-carbon alternative. Then vertical integration of indigenous low-carbon energy technology supply chains. By integration, we mean like the producers and the consumers of these low-carbon technologies should be based in India itself, and then unlocking the full potential of bioenergy economy. So this is our renewable energy program. As you can see in both the wind auction and solar auction tariffs, by 2026, India has the lowest auction. India is one of the lowest. India is one of the countries is, with one of the lowest auction rates across the wind and solar tariff systems. So India has a unique opportunity to leapfrog to a clean energy infrastructure. Like you can see the auction rates for many of the advanced economies around 3 to 4 times of India. So the renewable power is much cheaper in India than the other countries, and that will help us in uh, proliferating our renewable sources. And the fossil fuel supplies going to the power supplied from the fossil fuel, that share is going to come down, and the renewable share is going to increase in the coming years. But the challenges with renewable integration are it has a very short gestation period. So there is need to be planning and development of evacuation system based on potential renewable energy zones. Like renewable generation plant. An earlier session, the other speaker was talking about 15 to 20 years for a generation plant to come up. But the renewable plants are coming up in about 6 months to 10 months timeline. So there is a very short gestation period from planning to development. So the corresponding transmission evacuation system also needs to be planned much early, because the transmission network takes about 2 to 3 years from planning to development. So if the both are planned together, the transmission will lag behind, and we cannot get the full advantage of that generation. So transmission networks have to be planned around 2 to 3 years before a generation needs to come up. Then these sources are also intermittent, so they require by intermittent, that is that they have a variable output. There is no fixed forecasted duration in which those supplies will be up. Like a solar can be down anytime once the cloud cover goes once the covers the sun. So we need ancillary support services and for accurate forecasting of renewable output. So for these, we have these statcoms into our grid. The SVCs there in our grid, and nowadays we are also going for grid forming statcoms. So these statcoms will automatically change the voltage and frequency conditions in the grid depending on the solar output or the wind output or the renewable energy source output that are feeding them. Then there is also balancing of resources. So there is a need of creation of battery energy storage systems and dynamic reactive power compensators, and synthetic inertia from inverter or wind turbine grids, and then energy storage systems and synchronous condenser. The mitigation measures are so one of the other challenges are right of way. So now many areas in India are getting urbanized. So more and more urbanization leads to less land available for developing these large transmission systems or generation systems. So the right of way is getting very squeezed out. So the solution is to go at more and more higher voltage levels. So like if you have to transmit 1000 megawatt of power from point A to B, the land required for transmitting that power in a 1200 kV network is 1/4 of the land required to transmit that power through a 220 kV network. So higher the voltage levels, lower the cumulative right of way required to transmit the same amount of power. And then with the STLS line, the high temperature, low sag lines are going to be introduced. Multi-circuit towers are, so entire Delhi, there is a decision now to convert all the 400 kV lines on a multi-circuit tower or try to go for pole structures in the next 5 years. Then STATCOMs and PACs to control the grid instability. Then in terms of land acquisition, to resolve the problem of land acquisition for these new projects, we are going to come up with GIS substation, digital substation, and hybrid substations. In terms of renewable integration, now we are going for transmission to lead generation by around 1 year, strong interconnection for large balancing area, establishment of renewable energy management centers for renewable forecasting and scheduling, and also energy storage systems in a huge way. Like recently, you would have read that Andhra Pradesh has come up with a big project for energy storage, and it is the first state that has come up with this huge quantity of about 10 gigawatts of energy storage systems to be created in that state. Then, in terms of grid management, we have the smart grid real-time monitoring system with self-healing, wide area monitoring systems through PMU and in the URTDSM project, and automation of substations. So by 2047, these are the numbers. We will have the installed capacity 4 times that of now, around 2100 gigawatt, and solar will contribute around 40% of the installed capacity, and 47%, and then combining solar, wind, hydropower, and the nuclear, all the renewables are going to contribute to around 75 to 77% of the entire Indian power of the entire installed capacity in India. The peak demand is going to be around 708 gigawatt, and annual consumption is going to rise to about 3000 kilowatt hour per capita. The key challenge is transmission. We have already seen construction, right of way, land acquisition, compressed time schedule. System issues are maintaining high availability and reliability, and healthiness, to maintain healthiness of these assets across vast geographical area, and delivering 24/7 reliable and quality power in cost-effective manner. And then operational issues are protection against cyber physical attacks. So with more proliferation of digital systems, the vulnerability of these systems to cyber attacks also increases. Then there is a requirement of very skilled manpower in construction, O&M of new technology, and fund arrangement for new capital expenditure. So the technology initiatives that are under progress are this asset performance management system, a unified system for asset performance of the entire network. Then dynamic line loading, we have already carried out one of the pilot projects, and now we are going to implement it across, we are trying to implement it across more transmission corridors. Then green gas in place of SF6. SF6, we have seen that in 1990s, early 1990s, SF6 was introduced as an insulation medium in our circuit breakers, but these have very high environmental footprints. It's like 1 kilogram of SF6 has 32,000 times more poisonous than 1 kilogram of CO2. So we are now coming up with green gas in place of SF6 in our transmission assets. Then offshore substations are under planning stage, where we are going to create substations around 100 kilometers or 200 kilometers from the mainland. Then insulated tower cross arm to create so these insulated tower cross arm helps to reduce the right of way that is required for a transmission infrastructure. And then drones and robots are going to come up in a huge way by 2027 in condition monitoring of assets, then augmented and virtual reality, and green hydrogen and energy storage systems. So the transition of transmission infrastructure is shown here. We are going to move from a human-based grid to a machine-based grid. So now we are having in generation, we are having very large plants in a few pockets across the country. But with the government pushing on creation of micro generation centers through various schemes, we are going to have many smaller plants with low or zero inertia across the entire country. Till now, the grid was centralized, national, and energy-only market. But now we are going for a decentralized grid with coming up of these micro generators and with regional control and two-sided market where both the, so till now, the prosumer was producing energy for consumption by the consumer, but now with the coming up of these micro generators, even the consumer can feed the energy back into the grid for others to utilize. So it will be a two-sided market. And then transmission, we had very large power lines, but now with coming up of these various generate micro generators, we are going to have more smaller power lines with varied topologies and integrated storage system. In distribution, we are going from one point to two. Was passive. It was only in medium.
I request participant to please mute yourself. It's an earnest request from the participant to please mute yourself.
But now the consumer is where he can pay for the electricity use.
Dr. Patil, sorry sir for the interruption. Now you can continue.
Yeah, so now the consumer is also going to earn for the electricity that it sells to another consumer. So there is a initiative known as India Energy Stack. So like you are using Paytm to pay money to any account, any of the bank accounts, or you're using UPI to pay for any type of transaction, financial transactions. In coming 2 to 3 years, there is going to, through the creation of this India Energy Stack, each consumer is going to be a generator of electricity. So like if you have solar installed on your rooftop, solar power, and you have if it is 2 kilowatt unit, and you know that you are going for a long holiday and that 2 kilowatt is not going to be used, you can sell that power to your neighbor itself through your own mobile. So you can sell it to your neighbor, and the neighbor can pay you the charges for the extra electricity that he uses. So that is a concept that is still in concept stage and testing stage, and it is going to be tested in Delhi in a short while, and then replicated across India in the 2 to 3 years. Then we also have the concept of one sun, one world, and one grid. So like you see in the figure, these are the solar availability times across from Southeast Asia to Northwest Africa. And there is a 6 hour gap in solar peak from Southeast Asia to Europe. Like in Vietnam, if the sun is at its peak at 12 o'clock, in Europe, that is 6 a.m. And then in Europe, if it is 12 o'clock in the afternoon, in Vietnam, it is 6 p.m. in the night. So there's an opportunity to use solar energy 24 hours in a day, and with clean energy transition to anywhere and anytime. So for that, all these grids need to be interconnected with two-way power supply scenario. So this is the plan that is being created. So this BIMSTEC energy ring, where we are utilizing high RE capacity in India. There is high gas potential in Bangladesh and hydro potential in Nepal and Bhutan. So this grid is already connected, this BIMSTEC energy ring. And we have also seen that the plans to connect India with Oman are underway. So in Oman, that is a GCC IA ring, Gulf Council Interconnector Connecting Authority. Then the region of Afghanistan, Pakistan, Iran, Turkmenistan, they are connected by this Central Asian South Asian connector, this CASA 1000 project, which utilizes high RE capacity in Afghanistan, Pakistan, and surplus hydro in Kyrgyzstan and Tajikistan. Then there is a regional grid called as Unified Energy System of Central Asia, where Kyrgyzstan, Tajikistan are interconnected with Turkmenistan and Uzbekistan grid. In coming to the East Asian region, there is a grid that is getting formed in the form of GobiTech, where China is getting connected with Korea and Mongolia. There is high RE and hydro potential in China and solar potential from the Mongolian desert. And this GobiTech is getting connected to ASEAN grid. ASEAN is the Southeast Asian region. So ASEAN grid is already existing so various countries in ASEAN region are already interconnected, like Vietnam, Laos, Cambodia, Thailand, and Myanmar. They are already interconnected. So once we have this interconnection from ASEAN to India, like earlier you saw that India-Myanmar connection is under planning stage, the HVDC connection. So that will help connecting ASEAN grid to the Indian grid. Once the India-Oman interconnection comes up, then the whole Southeast Asia to Middle East region will get connected. And India is not going to be connected with Afghanistan or Pakistan through Kasa grid. That interconnection, so power flow is not in planning stage at that stage. So for Indian power, the power we are going to be connected with the Southeast Asian region, the Middle Eastern region, and then the Middle Eastern grid is getting connected to the European grid through this. There is a interconnection of Saudi Arab, Egypt, and Italy, which is already in planning stage. This is the HVDC connection. So once all these connections come through, power can flow from Southeast Asia to Europe within a single day. And India will act as an energy bridge between all these different grids. So what will the impact of this Asian grid interconnection? There will be efficient utilization of sub-regional energy sources. So it will lead to lower cost of electricity. There will be economy of scale and new renewable power supply and storage systems. So we'll be moving towards net zero emissions. Then social and environmental gains will be there. There will be inclusive electricity for all and associated services, and also optimization of energy mix and reduction on the fuel imports. We will have improvement in cash flow reserves. By 2032, there is a projection by Central Electricity Authority in India that we will be requiring around $108 billion of investment in the Indian power sector to create all this transmission infrastructure. So it requires strategic planning and significant investments. Government has taken various policy measures for a future-ready electric grid. In terms of generation, it has gone for national solar mission targeting 300 gigawatt solar generation by 2030. National hydrogen mission is there. Then PM Surya Ghar financial support for rooftop solar generation, which came up last year. Then renewable purchase obligations have now been extended up to 2030, and separate renewable purchase obligation is there for decentralized RE generation. In terms of transmission, government has gone for green energy corridors. So there are various green energy corridors being built across Rajasthan, Punjab, Haryana, Gujarat, and then also in the southern part like Andhra Pradesh, Karnataka, Tamil Nadu. They are all green energy. So entire states are being infrastructure is being created to feed green energy power to entire all these states. And now there is also a plan to create these green energy corridors in the states of Bihar and Bengal, and it is going to come up in the next couple of years. Then this northeastern regional power system strengthening scheme and this comprehensive sector strengthening scheme for Arunachal Pradesh and Sikkim to strengthen the Northeast India's transmission grid. Then also work to connect and create an interconnected grid from Southeast Asia to West Asia, and viability gap funding for offshore grid. In terms of distribution, we have this integrated power development scheme for digitizing of distribution infra, National Smart Meter Program, Ujjwal, you already know about this Ujjwal and Uday. These are roads schemes which are still in operation, and restructured accelerated power development and reforms program. This is the last slide now. So this is how the future energy grid is going to look around 20 years from now. It will be digitized, secure, and resilient grid. Electricity will be the main energy carrier. So till now, the main energy carrier is oil in India, but with proliferation of all these electric systems, electricity will be a major energy carrier. It will be decentralized and multi-vector energy grid, so there will be multiple sources of electricity. Then globally interconnected grid and inclusive and universally accessible grid. Thank you.
Thank you, sir, for an excellent and deeply informative session. Now we have opened the floor for the questionnaire. So I would like to request the participants to please move ahead with the questions. Question and answer round.
Okay, can I ask one question if the participants have no question?
Yes, yes. Move ahead.
Okay, I just want to know from Mr. Jha that Power Grid has taken a lot of Make in India initiatives. But I want to know that is there any making the initiative that is taken by the Power Grid of Corporation of India regarding the development of partial discharge sensors for in because right now the partial discharge is one of the emerging area for online condition monitoring of transformers, bushings, gas insulated substations. So I just want to know what is Power Grid thinking in this regard, and if there is any possibility to develop some indigenously developed PD sensors. Thank you.
Yes, so yeah, you're right that a partial discharge is a very important diagnostic methodology in transmission infrastructure, and there are already indigenous systems that are available in India with who are making these PD sensors, like Pacific Microsystems in Pune. They are developing handheld partial discharge units with UHF, TEV, HFCT, and acoustic sensors.
But none of the sensors are manufactured in India. They are all procured from Europe.
No, I don't think that is a right put. So they're not procured from Europe, but they are assembled in India. So like the chip still comes from outside.
Technology is from Europe.
No, technology. There are certain.
I work in partial discharge for more than 10 years. So I have never found any Indian company that has developed its own sensor.
So, sir, I can only tell based on the facts of the procurement that I have. Like we have, being a government utility, we cannot procure these sensors from outside. So, whenever we have done these procurement tenders, there are companies like RMI, which is Hyderabad based, which is supplying these sensors, and they are quoting it as a Make in India product. So for a government tender, you need to have at least 20% Make in India components. So like I said, entire SM product will not be manufactured, or not every component will be manufactured in India. So what they do is they procure the electronic cards from outside, and then they are assembled within India. So even RMI has its technology is being imported. The technology is being imported from Canada, but then they are making the sensors indigenously in India. That's what it is on paper, and that's what I can quote.
Okay, thank you. And do you have any idea about the dielectric spectroscopy measurement on the transformer bushings and power transformers? Are Power Grid thinking anything about to develop some online monitoring methods for tan delta assessment in power transformer bushings?
So so now these are two different questions. That the dielectric spectroscopy is a different technology, and online tan delta is a different technology. Dielectric spectroscopy, we have gone for dielectric spectroscopy, that is dielectric frequency response (DFR) technology, both for bushings and windings, and we have found them to be useful. But for online tan delta, we have tried with, I think, around 9 different manufacturers, 9 different kits, but we are not satisfied with the technology, so we discontinued a few years back. We tried all these technologies between 2014 to 2020, but they did not yield the required result. There was huge variation in the results with the offline testing results and the online measurements. Then they were also susceptible to different environmental conditions. And then, so because of the unreliable technology, we did not proceed ahead with that.
Okay, thank you. That's all from my side, sir.
Yeah, thank you.
Any
Nath,
further questions?
Yes, Mr. Nath, say one sun, one grid, one frequency. The phrases are very good to hear. In our country, as you also said, more than 20 hours it took for the grid synchronization, for making it one nation, one grid, one frequency. Now, can you tell us some problems? So some of the interconnections, as you said, already being done, right? So what are the problems you people are facing for these interconnections? Because only the synchronization part that may be done by the HVDC things. What are the other problems? If you highlight a little bit on that.
So once you go for these international interconnections or these OSOVO, the problems are multidimensional. There are technical challenges related to grid synchronization. Sorry, am I audible? Yeah, my mic is.
Yes, sir.
There are problems with grid synchronization where different countries operate at different frequencies and inertia levels and grid codes. So grid code of India, like country like Bangladesh, it did not have grid code until very recently, like about 2020, its grid code was not standardized. Then AC interconnection requires very tight frequency and stability coordination. So like with India, Bangladesh, there is an HVDC link, but there is also an AC link, that is Komala Surajmani Nagar and Behrampur Bharamara. These are AC links. So they require very tight frequency and stability coordination. So your grid is there at 50 years, but suppose say Bangladesh, if Bangladesh had 51 years, then it would be very difficult to integrate both these grids at a synchronous frequency range. Then there are stability and security risks. Disturbances can propagate across borders. Like last year, if you have heard about Iberian Peninsula blackout in Spain, Spanish grid was interconnected with France, with Andorra, with Portugal, and with Germany. So the problem that originated in southern Spain led to grid blackouts. Entire Portuguese grid was blacked out. There was problems also within in France, where the southern France region was blackout for around 30 minutes, and a line also tripped in Germany. So these disturbances, there needs to be proper islanding schemes that has to be created for uh, stability and ensuring security of different regional grids. And oscillations, low inertia, and weak grids can increase cascading failure risk. So why I talk about weak grids? So there is been an India-Sri Lanka interconnection. It has been in talks for the last 10 years. Now it has come up to a stage where both countries are ready to sign, because Sri Lanka is a very weak grid with uh, not much transmission scale stations. But India grid is a very strong grid. So once we connect India, Sri Lanka, and a fault occurs in Sri Lanka, that can propagate back to India. Then there are also protection and control mismatch. So we can have different protection philosophies, delay settings, and fault clearing times between different countries. So these are the technical challenges. If I talk about operational challenges, they are related to dispatch and congestion management. So there will be different priorities for domestic versus export power. What that if you are connecting your grid to a Southeast Asian grid, what amount of power will he be able to export? What is his priority on exporting to different countries? And it can lead to curtailment and redispatch costs. And then there is also data sharing and cyber security issues. So once the grids are in real-time data exchange requirement of SCADA, of PMU, and forecasts, will those countries be ready to support that real-time data exchange? And then there are also regulatory and market challenges. What is the price on which you will accept the electricity from a different country?
Yes, yes.
If that country itself, like in terms of India Nepal interconnection, like recently a line was charged, and it was in the news that we are going to supply Nepal power at 11 rupees per unit. None of the states that are surrounding the Indian states that are surrounding Nepal have this price, 11 rupees per unit. So now suppose tomorrow China tells Nepal that okay, we will supply you power at 5 rupees per unit, then Nepal will immediately disconnect the Indian connection. So there are pricing and settlement issues. There is currency risk. There is price volatility, and also long-term investment uncertainty. With like recently last in 2024, after the upheaval in Bangladesh, you saw that the line connecting Godda in India to Khulna in Bangladesh had to be terminated. So investors face risk from these policy changes and political instability in these countries, in other countries. And then there are geopolitical and strategic challenges. There is energy security concerns, political tensions, trust deficit. So these are all the challenges with creation of all these grids, and that's why it takes long gestation period, long terms of. There should be a political stability, diplomatic stability to create all these grids together.
Thank you.
Yes, any further questions? Okay, so we are closing the question and answer session. So now may I request everyone to please switch on the camera. We have to take the screenshot. I request everyone to please switch on the camera.
this session.
Done. Thank you.
So I would like to thank once again our resource person for giving his valuable time. Now with that, we formally conclude the academic proceedings for day one of the faculty development program. We extend our gratitude to all our resource persons and all the participants for their time, engagement, and enthusiasm.
All participants are kindly requested to submit their feedback using the two links. One link will be session one, and other link will be session two. So as we have shared the two links, so you have to submit two feedbacks. So one will be for session one, other will be for session two. Those who have submitted their feedback form, so you can leave now. Anshu,
Sir, where is this link?
नहीं ठीक है, तुम चला जाओ, कोई प्रॉब्लम नहीं.
Sir, can you please share the link on the WhatsApp group also?
No, it is not possible. Don't request same thing once again. So as it is a online platform, so we'll share the online only. Huh? Don't request the same once again. We have shared the two links many times, and reflected journal. So that will be we'll share this information soon. When you will submit the reflection journal. We have created the WhatsApp group to share the information only, not to submit the feedback form. So for your reference, I am sending the once again the link. And all participants are requested to submit the link from the laptop or desktop only, not from the mobile. And to get certificate, so four things are needed. One is attendance, another is assessment, another is feedback, other one is reflected journal. Assessment, bola to. Attendance, assessment, feedback, and reflected journal. Attendance is 80%, assessment 70%, online feedback from your Hotel account, and reflected journal. So that will be mailed to us, to our mail ID only. Mr. VSNK Chotina, how many times we will share the link? VSNK, please unmute, please. And what do you want to say? Tell me. Platform is open right now. VSNK Chotina.
Sir, I have used the link which was shared before, sir, but it is showing session 2.
How many times will tell you? The two links we have been given, and out of two links, one will be one, another will be two.
Yes, sir. Sir, actually, the same link I am using,
Two
sir.
links,
But
two links. No, the two links are different one. Huh? Although that session 2 is noted on side of the form, you have to submit two links. VS Chaitanya, keep in mind. Two links. As we have shared two links, you have to submit two links only. Using two links, feedback.
Okay, sir.
To submit the session feedback, we have shared two links, and two links are different. And you have to submit your feedback using two links. One link will be session 1, and other link will be session 2. Renewables, do you want to say something?
Sir, unable to get the feedback link, sir. Where it is, sir?